that we have discussed how AC voltage affects a circuit containing an inductor, a capacitor, and a resistor, we will now come to a topic called resonance. And before we start with the analysis of this phenomenon, let's get an intuitive idea of what resonance actually is. I'm sure most of you are familiar with the Indian musical instrument called the sitar. It's simply a box, and that box has a lot of musical wires. Each of those wires is at a different length and a different tension. Now, if you hit those wires with a plucker, each of these wires will vibrate at a different frequency owing to the differences in its length and tension. This natural frequency with which that wire reacts when you hit it is called the natural frequency of that wire. And it is not just true for musical instruments. Any system in nature which has the oscillation phenomenon, it can be the pendulum in a clock, it can be a suspension bridge which sways back and forth. Any system which displays oscillation will also display the quality of resonance. There will be some natural frequency for that structure or that system at which it will vibrate with maximum amplitude. Now, you could ask, what do we require for resonance to take place? In any system that is undergoing oscillation, there are at least two forces involved, or at least two agencies involved. The balance between these two forces decides the maximum amplitude and frequency for that particular system. Both of these agencies have to be able to store energy, and the resonance phenomenon is happening because of the interchange of energy between these two agencies. In an LCR circuit, the resistor does not store any energy. A resistor, as you already know, can only dissipate electrical energy. But there are two elements in an LCR circuit which are storing energy for some amount of time. We have the inductor, which stores energy in the form of a magnetic field, and we have the capacitor, which stores energy in the form of an electrical field. Now, these two elements, the inductor and the capacitor, are continuously trading power or energy with each other because they are operating out of phase. This energy is being transferred from the capacitor to the inductor and vice versa through the resistor. So we can say that for an LCR circuit, the current in it at any given time, let's call it Im, can be expressed in terms of the ratio of Vm, that is the peak voltage, divided by the total impedance of the system, which we denote by the letter capital Z. Please note, we are talking about impedance, so this comprises of both the reactances of the inductor and capacitor and the resistance of the resistor. Mathematically, we can define this as Vm divided by R square plus Xc minus XL whole square, where Xc is the capacitive reactance and XL is the inductive reactance. Let's recall what we had learned earlier. We already know that Xc is given as 1 upon omega C, and we also know that XL is given as omega L, where capital C is the capacitance of the capacitor, capital L is the self-inductance of the inductor, and omega is the cyclic frequency measured in radians per second. Now, there will be a particular frequency dependent on the values of the capacitance and inductance at which they will perfectly cancel each other out, which means that if you look at this equation, there is a particular value of omega where XL and XC become equal to each other. When this happens, the entire reactance component of this impedance goes to 0 and the reactance becomes purely resistive. So we no longer have the impedance of the capacitor or the inductor in the circuit at that particular frequency at which their reactances become equal. So we can say that there is some frequency omega naught for which 1 upon omega naught C becomes equal to omega naught L. So if we do some algebraic manipulation, we can say that omega naught square is equal to 1 upon LC, or in other words, omega naught is equal to under root 1 upon LC, and here omega naught is the resonant frequency for this particular system. What this means is that For a given circuit containing a definite value of the inductor and a different value of capacitor, there will be a particular frequency omega naught at which the value of Im, that is the current, will be maximized, because at that value of frequency, the reactances of the capacitor and inductor cancel each other out. We can see this graphically. If we were to plot the magnitude of the current as a function of frequency, we would notice that the current peaks for a particular value of frequency, which we define as omega naught. This is the resonant frequency of the system. And this phenomenon, resonance, is used in many places in electronics. Most of you are too young to remember the old days when we had a rotating knob for selecting the frequency on the radio or on the television set. What were we actually doing? By turning that knob, we were turning or changing the inductance or capacitance inside an LCR circuit. By doing this, we are changing the resonant frequency of that circuit, and that allows us to change the frequency at which the device is operating. So by turning that knob, you are changing the capacitance or the inductance within that circuit, and by doing this, you are changing the resonant frequency, and that change in resonant frequency allows you to select between different channels on your radio or your television. Now you could ask me the question, what is the role of resistance in this case? Now, as I told you before, a resistance cannot store energy inside it. It can only dissipate the energy inside it. And it will also limit the peak value of current within this resonant system. So if I were to increase the value of resistance in a given LCR circuit, keeping everything else constant, I would notice that resonance still occurs at the same frequency, but the peak is much less sharply defined. In other words, the peak amplitude of current is now lower than before because of the increased resistance. Also, the selectivity of the circuit is also less than before, because as we see, the peak is not very sharp. It is spread out over a larger range of frequencies. So for any resonance system, if you increase the amount of resistance, the selectivity of the system goes down, the peak of the resonance becomes less sharply defined. So ideally, an excellent resonance circuit which has perfect selectivity would ideally have no resistance and very high values of inductance and capacitance.
Manorama Horizon. Learning made simple.